Hello everyone, my name is Komal Pandey,
And I am open here.
and today we will be forming a parse tree out of an equation. And this is a question that I have given home to solve.
So let's take plus first and x. Let's take this equation next. Then it's multiplication and with y and z. Then it stays with w. So this is the parse tree of this equation. Now this equation is given by me to cook.
Firstly, we take multiplication. We have 5 on the left hand side. Then this equation, we take plus x on the left hand side. Then this equation will come on the right hand side. We have division over here. And on the left hand side, we have y. Over here this. So we take minus z minus 10. So it will be z over here and 10 over here. So this is the parse tree for this equation.
So today we learned that if given any equation, we can make a parse tree out of it. So that was it. Thank you.
Thank you.
Hello everyone, my name is Komal Pandey,
And I am Om Pednekar.
and today we are presenting a research paper review on verified executable parsing by Aditi Bartwal and Michael Norrish, published at ESOP 2009. This paper is part of our operating systems and compilers subject under the guidance of our mentor Nilesh Lakre. Let's get started. So, the first question this paper asks is why do we even need to verify a parser? Think about it. A parser is the backbone of every compiler. It takes source code, passes it through Alexa to get tokens, and then it builds a parse tree. But here's the problem. How do we trust that the parser is correct? An incorrect parser can silently accept wrong programs or reject perfectly valid ones. And the scary part is, traditional parsers are just built and assumed to be correct. No one actually proves it.
And that is exactly the gap this paper fills. It asks, can we mathematically prove a paper is correct? Specifically, it raises two critical questions. First, if a parser produces a parse tree, is that tree guaranteed to be valid with respect to the grammar? And second, if a string belongs to the language of the grammar, will the parser always find it? These two questions form the foundation of everything this parser proves.
Before we get into the parser itself, let's understand the foundation, context-free grammars, or CFGs. A CFG has four components. Terminals, which are the actual tokens like numbers and operators. Non-terminals, which are abstract symbols like expression or statement. Rules that map non-terminals to sequences of symbols. And a start symbol. In the paper, this is formally defined in HOL4, where a symbol is either a terminal, TS, or a non-terminal, NTS. A rule is simply a mapping from a string to a symbol list, and the language of a grammar is a set of all terminal strings you can derive from the start symbol.
Three key concepts flow from CFGs that the paper formally defines. First, nullable. A sequence of symbols is nullable if it can derive the empty string, written as alpha derives epsilon. Second, the first set. The set of terminals that can appear at the beginning of strings derivable from a symbol. And third, the follow set. Terminals that can immediately follow non-terminal in any derivation. These three, nullable, first, and follow, are critical because they are used later to build the SLR parsing tables. Parse trees. Now let's talk about parse trees, the central data structure in this entire paper. A parse tree represents the syntactic structure of an input. The root of the tree is always the start symbol. Internal nodes are non-terminals and the leaves are terminals. The actual tokens from the input. For example, for the expression 1 plus 2 times 3, the parse tree shows that multiplication has higher precedence than addition through the tree structure itself.
The paper formally defines what it means for a parse tree to be valid with respect to a grammar. A tree node is valid if there exists a rule in the grammar where the root non-terminal derives exactly the symbol at its child nodes, and recursively. All subtrees must also be valid. This is captured in the valid p-tree function. Two key properties must hold. First, the parse tree must be built using only grammar rules. Second, reading the leaves from the left to right must give back exactly the original input string. These two properties become the basis for all the soundness and completeness proofs. Moving on to the next slide. Now we come to the SLR parser itself. SLR stands for simple LR. It is a bottom up parser, meaning it reads tokens from left to right and builds the parse tree from the leaves upward. It uses a push down automaton, basically a stack machine, with states and a stack. The key idea is that each state in the automaton corresponds to a list of items. An item is a grammar rule with dot in it. The dot shows how far we've progressed in recognizing that rule. For example, n arrow alpha dot beta means we've already seen alpha and we are now expecting beta.
Based on the current state and the next input symbol, the parser performs one of three actions. Shift, push the next token onto the stack and move to a new state. Reduce, when a complete rule is recognized, replace it with the left-hand side non-terminal, or error when neither is valid. Reject the input. The paper formalizes this through two key functions: the goto function, which takes a state and a symbol and returns the state, and the reduce function, which tells the parser which rule to apply. Using just these two functions, the entire SLR machine is defined. Constructing the parser. So how is the SLR parser actually built? The paper defines a function called SLR map. The SLR machine constructor, it works in 5 steps. First, the grammar is augmented, a new start symbol and an end of file marker are added so the parser knows exactly when it's done. Second, closure is computed. Given a set of items, we expand it by including all items for non-terminals we expect to see next. Third, next state computes the next automaton state by moving the dot over a symbol and taking closure.
Fourth, the reduce table is built. For every complete item where the dot is at the end, we check the follow set of that non-terminal. And if the next input is in that set, we reduce. This is what makes it SLR specifically, using the full follow set. Finally, the most important step, conflict checking. If for any state and input symbol, both a shift and a reduce are valid, that is a shift reduce conflict, and the grammar is rejected. Same for reduce conflicts. Only if there are zero conflicts does SLR MAC return a valid automaton, and that's a guarantee of correctness. So, this is the heart of the paper. The authors don't just build a parser, they prove it is correct using the HOL4 theorem prover. This took 7 months and involved over 700 lemmas and 21,000 lines of proof code. They prove three major properties. Theorem 1 is validity. The output parse tree is always built using only rules from the grammar. Theorems 2 and 3 together give soundness, and Theorem 4 gives completeness.
Think of it as three pillars holding up a verified parser. Soundness says if the parser accepts an input, that input is genuinely in the language. No false positives. Completeness says if an input is in the language, the parser will find a parse tree. No false negatives. And together, these prove the parser is both correct and thorough. There is always a corollary, non-ambiguity, which we'll see next. Let's look at soundness in detail. Theorem 3 says if the parser produces a parse tree for input S1, then S1 belongs to the language of the grammar. The proof has two parts. First, it shows that the leaves of the parse trees equal the original input string. Nothing is added or dropped. Second, it shows that having a valid parse tree is equivalent to the string being in the language. Together, these confirm the parser never accepts something it should not.
Completeness. Theorem 4 says if a string is in the language of an SLR grammar, the parser will terminate and return a parse tree. The key assumption here is that there are no useless non terminals. Every non terminal must be able to generate at least one terminal string. The proof uses induction. The critical lemma supporting everything is if there exists a rightmost derivation of a word W, then the SLR automaton takes a sequence of shift and reduce steps that exactly mirror that derivation in reverse. This connection between parser execution and grammar derivations is the deepest insight of the paper. Okay. So the grammar is ambiguous if one input string can produce two different parse trees. This is a serious problem for compilers. If the same code can be interpreted in two different ways, you can get unpredictable behavior. Look at the example on the slide 1 plus 2 times 3, which was explained by Ohm. An ambiguous grammar might give two valid parse trees, one where addition is done first and one where multiplication is done first. The compiler wouldn't know which meaning is correct.
The paper proves that SLR grammars are always unambiguous as a corollary of soundness and completeness. The logic is elegant. Since the automaton is deterministic, no conflicts allowed. It can only follow one sequence of steps for any input. Therefore, there can only ever be one parse tree. This is formally defined in HOL4 as for every word in the language, all derivations must be identical. The practical value is huge. When SLR Mac succeeds in building an automaton for your grammar, you automatically get a proof that your grammar is unambiguous for free. Here's an interesting engineering challenge in the paper. The mathematical HOL definitions are beautiful and easy to prove things about, but they use existential quantifiers and transitive closures, which computers can't directly execute. For example, the nullable function is defined as S1 derives the empty string in 0 or more steps using the transitive closure operator. A computer can't just run that definition. So the authors had to create executable counterparts in SML, standard ML, and then formally prove these SML versions behave identical to the mathematical ones.
The executable version, called nullable ML, works by explicit recursion. It checks each symbol in the sentential form, and when it hits a non terminal, it recursively checks all its right hand sides to prevent infinite loops from circular grammar rules. It tracks a scene list of non terminals already visited, proving termination required a lexicographic measure. Either the number of unseen non terminals decreases or the sentential form gets shorter. One of these two must strictly decrease at every recursive call, guaranteeing the function always terminates. This bridging between mathematical elegance and executable reality is one of the most technically interesting parts of the paper. To conclude, this paper presents the first machinized formal verification of an SLR parser generator in HOL4. The authors proved soundness, completeness, and non ambiguity using over 700 lemmas in 21,000 lines of code, taking 7 months. They also bridged the gap between formal mathematical definitions and actually executable SML code. For future work, they propose extending these proofs to LALR and LR1 parsers, proving termination on all inputs and computing tables statically for performance.
The four key takeaways from this paper are: 1. Parsers can be mathematically trusted, not just tested. 2. CFG derivations and parse trees are the absolute building blocks of all parsing theory. 3. SLR parsers hit the sweet spot, deterministic, conflict-free, and provably correct. And 4. Formal verification in compilers matters deeply because one silent bug in a parser can corrupt every program it compiles, as the paper shows. A verified parser doesn't just work, it proved to work. Thank you.
Thank you.